So another way of doing integration through algebra is known as partial fractions. We'll need to define some terms. Let f of x and g of x be polynomials. The rational function f of x over g of x is a proper rational function if the degree of g is greater than the degree of f. It is improper otherwise. And one useful idea is that if we do have an improper rational function, we can use polynomial division to transform it into a polynomial plus a proper rational function. This leads to the following. Suppose I have two or more rational expressions. We can use the standard rules of algebra to add them to produce a single rational expression. But equality works in both directions. And what this means is that we can take a single rational expression and write it as a sum of rational expressions. This leads to the following result. Suppose I have a proper rational function where the denominator is expressible as a product of two polynomials. Then we can always produce a partial fraction decomposition where the degree of each numerator is less than the degree of the denominator. So let's try to find a partial fraction decomposition. Since we're starting with a proper rational function, our theorem guarantees we can write this as a sum of proper rational functions where the denominators are the individual factors. Here, because both denominators are degree 1, this means that the numerators must be of degree less than 1. They have to be constants, and so we'll call them a and b. We'll multiply both sides by the common denominator x minus 3 times x plus 2, and simplify down to a final expression. Now, it's important to understand that the equals in this case means that we want the rational function to be absolutely, completely 100% interchangeable with this sum of rational functions. And that means that 5 must equal a plus bx plus 2a minus 3b for all values of x. And that means that the coefficients of the variables on both sides must be the same. So, over on the right-hand side, the coefficient of x is a plus b. So, I need to make that equal to the coefficient of x on the left-hand side, which is 0, because over on the left-hand side there is no x, and so the coefficient must be 0. Similarly, on the right, I have my constant term 2a minus 3b. This must be equal to the constant term on the left, 5. And now this gives me a system of two equations with two unknowns, a and b, and I can solve that system of equations. And I have a equals 1, b equals negative 1. And again, this is the correct way to solve for a and b. However, the usual way of solving this system is slightly different. And this is based on the idea that we need this equation to be true for all values of x. Or, since this equation came from the preceding equation, we need this equation to be true for all values of x. So, what's a good value of x? Well, notice that if x equals negative 2, this first term drops out, and so we get the equation, which is an equation that's much easier to solve for one of the variables. How do we get the other variable? We'll choose a different value of x, and a convenient value of x to choose is going to be x equals 3, because that's going to make this second term drop out. And if I let x equals 3, we get the equation, which is again much easier to solve for our variables. And we have the same solution, a equals 1, b equals negative 1. Now, before proceeding, we might want to think about why we can't actually do it that way, but why we still do it that way. So remember that our original equation was, and in this equation, x can never be 3 or negative 2. And so when we dropped x equals 3, x equals negative 2, and produced an equation in A and B, we were taking advantage of a situation that could never exist. So why did it work? Part of the reason that it worked is that any value of a and b that satisfies this equation for all x other than 3 or negative 2 will also satisfy this equation for all x other than 3 or negative 2. So again, all we really need to do is to find an a and b that satisfies this equation for all x other than 3 or negative 2. Well, we did one better. We found an a and b that satisfies this equation for all x, which means it will certainly satisfy our original equation for all x other than 3 or negative 2. It's important to understand that everything up to this point is just algebra. We've done no calculus so far. So let's go ahead and introduce a little bit of calculus and talk about the antiderivative of 5 over x minus 3 times x plus 2. Because the denominator is in factored form, we can find the partial fraction decomposition. Actually, we've already done that. And the additivity of the antiderivative means we can split this integrand into two integrands and evaluate each one separately. So we'll use a u substitution. For the first integral, we'll let u equals x minus 3, so du is dx. Making our substitutions, integrating, and we'll put everything back where we found it. And to take into account the fact that you can't take the log of a negative number, we'll throw the argument x minus 3 into a set of absolute value bars. Similarly, for the second integral, we'll let u equals x plus 2, and then du will be dx. We'll make our life easier by factoring that negative 1 out front of the integral. We'll make our substitutions. We'll find the antiderivative. We'll put everything back where we found it. And again, because this is log, we'll want to take the log of the absolute value of x plus 2.